Hello, this is Brian Washburn. I'd like to give an introduction to mechanics and non-inertial reference frames. So far, every problem we've done in class is using an inertial reference frame, and that's a reference frame that doesn't accelerate. So this is a reference frame that either doesn't linearly accelerate or rotation, because rotation is also an acceleration. And the reason why we've done that is because Newton's laws are only valid in inertial reference frames. However, in some cases and problems, it's not very convenient to use an inertial reference frame. For example, if I consider the Earth, if I have a problem where I'm on the surface of the Earth, okay, I don't want to have to pick a reference frame that's outside of the Earth to do my problem, okay. And so what I want to do is I want to pick a reference frame that is on the surface of the Earth. However, the Earth rotates. The Earth has a pole, and then it has an angular speed, and then angular speed we can represent as a vector, okay? And there's a magnitude and direction of that. The magnitude is going to be along the axis of rotation, so this is what I'd call the North Pole. I have a pole that kind of goes through, and so that is the direction of the angular, the direction of the angular velocity for the Earth, okay? Now, what is the speed? Well, the angular speed, or the magnitude of the angular vector velocity, is going to be, well, it does 2 pi, okay, in a day. So there's 24 hours in a day, and there's 3,600 seconds per hour. So that gives me angular speed. The angular speed for the Earth is 7.3 times 10 to the minus 5 radians per second. Now, that's pretty small. Relatively speaking to things, if I spin a basketball or something like that. So when I do projectile motion, normally I don't see these so-called non-inertial terms. Okay. However, if I do projectile motion over long distances, you see them quite a bit. And so that's what I want to do is we want to solve, for example, projectile motion on the Earth over long ranges to take into account of these other effects of the fact that the Earth is rotating. So what I want to do is, okay, so far, say I have, let's consider 2 reference frames that kind of shown in the picture. S0 is an inertial reference frame. Okay, it's this fixed and doesn't do anything. But then I have a second inertial reference frame. I'm going to call a non-inertial reference frame. I'm going to call the S0. This is my non-inertial reference frame. Okay. And so for my particular case, I'm going to say, let's fix that reference frame with respect to Earth. It's going to rotate at some, and here I kind of show in a picture, I kind of show that that reference frame has an angular velocity respect in space. And so S is going to kind of rotate about S naught. Now, if I write down my equations of motion, let's just go back to Newton's laws, okay? Newton's laws will tell me that mass times acceleration is equal to the net force. However, if I write it like that, I only can write that properly in the S naught reference frame. Okay? And the reason why is because that's the inertial reference frame. But what's going to happen? But I don't want to do that. I want to write this in terms of a reference frame that moves on the Earth, or a rotating reference frame. So really what I want to get is not, I want to get mass times acceleration, but I express that derivative in the S frame. So what am I going to get? Well, what I'm going to get is I'm going to get something that looks like F equals ma, but there's going to be other stuff. Okay, there's going to be other stuff that's left. So instead of representing my acceleration in S naught, I express my acceleration in S. There's going to be some extra terms. I'm going to take them from this side of the equation and bring them over here, and I'm going to call these things forces. Okay, and these are what I would say these are called forces with exclamation with apostrophes or whatever quotes there, and because they're not really forces. Okay, they are things I call forces, and basically the idea is that I like F equals ma so much that in a non-inertial reference frame, I'll make up forces, okay? And I'll get some extra terms, I'll throw them on the right-hand side equation, I call them forces, all right? Even though they're not really forces. In the end, what are these things going to be for us? Well, what they're going to be, and what we're going to show for a rotating reference frame, is that I'm going to get 2 terms that I'm going to call forces. Okay, and the first term is what I'm going to call an centrifugal term, which we've seen already in class. And the third term is what I'm going to call a Coriolis term, which we haven't seen, but we'll see that. So that's in the end what I want to do. Okay. Now, how do I want to do this? Well, the thing is this. Say I have a general vector Q. Okay, Q is this a general vector? For us, that could be a position vector or a velocity vector. Okay. What I want to do is I can write the rate of change of Q in a reference frame called S. That's the rotating frame. But however, I want to relate that to the rate of change of Q in the non-rotating frame S naught. So I want to get some relationships between those two. And the reason why I want to do that is because eventually I have to take not d dt, but the second derivative of Q, because I expressed the acceleration. So that's what I'm going to do. So let's start that derivation. Okay, so let's consider a coordinate system x, y, and z that's in the S reference frame. So that is my rotating reference frame. Associated with that is x hat, y hat, z hat. And I can, again, using similar notation, I'm going to call that xi hat. All right. Again, those are in the rotating reference frame, and so they move. So basically, x hat, y hat, and z hat will be functions of time. And then for Q, I can always write Q as a sum, in that reference frame. For example, Q in that reference frame would be, x sum. I can sum over those guys to 3. I can always represent Q in that reference frame. Now, before I do that, remember, I have to start off in the fixed reference frame, because remember, I want to start with ma equals F, and the only way I can write force equals mass times acceleration is in the fixed reference frame S naught. So let's first start looking at the rate of change of Q dt in the S naught frame. That's the fixed frame. Okay. So what I have to do is, remember, Q can be represented, however Q is and I have to represent that in terms of x hat, y hat, z hat. So I have to sum over, so the components of Q, dqi dt, and then that's in the x hat, y hat, z hat direction. So remember, I is 1, 2, 3. However, x hat, y hat, and z hat, they change. And so using the chain rule, I have to sum qi, the rate of change of the position vectors, looking at it in the fixed reference frame naught. So now what we have to do is we don't want to express the derivatives all in terms of S naught. We want to represent them in terms of in the S frame. And so the question is, what do we do with this thing here? So now we've actually looked at rate of changes of Cartesian position vectors before. And here's a more general result of that discussion. We did this earlier in a class. I can show that the rate of change of xi hat is going to be equal to, if it's rotating with some angular velocity omega, it's going to be equal to the cross product of omega times xi hat, the rate of changes. That's interesting. You may say, why is that? And we've shown this not in a vector form like this, but we've actually derived this before when we derived the, for example, velocity and acceleration in spherical and cylindrical coordinate systems. But here I can kind of explain this with a picture more than anything else. So say at some time t, I have xi hat at t. All right. And then say this thing rotates with an angular velocity, and I'm going to write the angular. And at some later time, let me use a different color. I'm going to have, at an instant of time later, I'm going to have another vector here of the same length, and I'm going to call that guy xi hat t plus delta t, so some instant later. Okay. Now, if I subtract those two vectors, I'm going to get, again, I'm going to get a vector that's going to be perpendicular to both of them. And what is that guy? Well, that's the difference between the two divided by time. Okay. Well, that is just xi hat dt. And you can see that this general relationship is true. If I take if I take my fingers and point it along the direction of xi hat, so I take my fingers and point them in this direction and curl them up, my thumb will point. Sorry, I did that wrong. So if I point, actually I got this right. It says a little weird. I take my fingers and point them along the direction of omega. I curl them in the direction xi hat, and my thumb will point along the direction of dxi hat dt. So this is a general relationship. So what that's going to do is it's going to allow us to basically take this thing here and substitute omega in there. Now remember, our system isn't moving with little omega, it's moving with capital omega. Okay, so let's use that result and write down. So what I'm going to do is I'm going to look at this term here, and let me write that term there and use that result. I can say that the sum, okay, of qi, again, I'm just looking at that one term, dxi hat dt in the S naught fixed frame is going to be equal to a sum of qi's, and then here I'm just going to stick in, remember the system moves with capital omega, xi hat. Okay, that's using that result there. But then I can use a commutative property of the cross product. I can just bring out omega, and then I'm going to sum over qi xi hat. Okay, but that's just equal to q in the, remember that's q in the rotating reference frame from this result right here. Okay, so we got a very general result, a really very important, cool result. Okay, so then, okay, but the last thing I forgot to mention, this thing here. So we just looked at this term here and showed it's equal to that. And what is this? Well, dq dt, that is just the rate of change of q in the, and since the xi hat is in the S frame, this thing here is just the rate of change of q in the S naught S frame. So what have I shown? What I've shown is that dq dt in the S frame, S naught frame, is equal to the rate of change of dq dt in the S frame plus omega cross q. That is our main result, and we're going to use that multiple times. Does it make sense? Well, if the frames don't rotate, then omega is equal to 0, and then the rate of change in one frame is equal to the other. So that's cool. Now, to make things a little more convenient, notice that q is completely arbitrary, and so instead of writing this as a complete derivative, I'm going to write it as an operator, and I can say for my operator that d dt, that's an operation in the S naught frame. I can relate that to d dt in the S frame plus omega cross whatever. So that is an operator, and so that's another result that's important. It's basically the same result, but instead of writing it as a complete thing, I write it as an operation. Okay, now why do I want to do that? Well, remember, what next thing I'm going to do, remember, I want to say m r double dot in the S naught frame equals f.
and I want to write that in the S frame. That's what I want to do. So let's do that next. Okay, so now we're ready to finish the derivation. What we're going to do is we're going to start off as mass times acceleration. We don't want a dot. I can't put a dot and a dt in there. What I'm going to do is this. So this is my starting point, and that is in the S0 frame, because that's the only frame I can write this equation. Okay. Now what I want to do is I want to express that second derivative, this guy here, and sorry, there's a 2 there, can't forget that. I want to express that derivative in the S frame. Okay, so I have to write this. So what is that? Well, that's going to equal to d dt. Now, again, this is a second derivative, but I always write the second derivative as two first derivatives. Okay. Okay. So now, for this guy here, I'm going to use this. And then for that guy there, I'm going to use this kind of operator notation. So I can write this as, let's do this part first, and then we'll do the second part, make it less confusing. So I get d dt of S naught times this stuff here. So I'm going to do this, and then here I'm going to put, instead of Q, it's R, of course. That's in the S frame. Okay. And then now I'm going to use my operator notation for that thing there. S plus omega cross, and that thing is going to operate on the stuff that's in the parentheses. And let me get rid of this stupid thing here. Apologize for that. The stuff in the parentheses is just what I have there to begin with. Okay. So now, notice, okay, so if I operate, let's think about this. So if I operate this on this, and let me, again, write it very completely. Okay, so if I take this on that, what I'm going to get is I'm going to get the second derivative of r dt. That's the second derivative. But that's in the S frame. Okay, so what is that? That's acceleration in that frame. And then what I'm going to do is I'm going to operate this. I did this on that. And I'm going to take this on that. Okay. So then that's going to give me omega cross this. Okay. Okay, so now I'm going to operate this onto this. Okay, now when I do that, you have to think, does omega change with time? Well, we're assuming that omega doesn't change with time, so it's a constant. So then I'm just going to operate this on that. Well, that's just dr dt. So then I can write that as omega cross dr dt. So I get the same expression. I get two of the same things. That's important. And then the final thing is I'm going to operate mega on this. So then I get kind of a triple cross product. Like that. Okay, so what is that? Okay, if I'm expressing the acceleration in my S naught frame, it's equal to a bunch of extra stuff that's in my S frame. Okay. And these two things are the same. Okay. So now that's my main result. And so now let's just stick that into. So let's tidy up the notation a little bit. Okay, just a little bit. So if I tidy up the notation, I can say that R double dot in the S naught frame is equal to R double dot in the S frame plus omega. Now we got two of those, so it's 2 omega cross, this is R. And by the way, okay, so just following your book notation, at this point your book actually drops out the S, okay? Because in the end, I don't care about the S naught frame. I just care about the S. So I'm just going to call that as R. That is by context in the moving reference frame. So then this sucker here is that. And then I get this weirdo triple cross product term like that. Okay. So now, to find, so basically what I said was, well, M times R double dot in the S naught frame equals F. I'm going to stick that result. I'm going to get M times R double dot plus M times 2 omega cross R dot plus M times this triple cross product here. Okay. Now, notice I have mass times equals F. Okay, so now if you can see here, this is the same force I had. This is the same force I had before, but now I got this extra stuff. So instead of keeping on the left-hand side, I'm going to move it to the right-hand side and rewrite. So I get a mass times acceleration is equal to, well, I have the force. And then when I bring this term over here, I get a minus sign. But remember, cross products are anti-commutative, okay? Sorry, let me get that. Okay, so let me summarize a little bit. So again, what I did was I have a rotational reference frame, rotating reference frame S that has vectors, position vectors x hat, y hat, z hat, which I'm going to just denote by xi hat. A vector q can be written in that in a normal way. When I wanted to write a derivative of q respect to s naught, that's the non-inertial, that's the non-rotating frame, the inertial reference frame. If I'm going to write this vector here, this rate of change here, what I'm going to do is I have to use a cross product or the cross chain rule to do this, and so I can say that's rate of change of dqi dt xi hat plus, and then of course there's a rate of change of the xi hats, okay, in the S naught frame, because if I was in the S naught frame, what I would see is those vectors are rotating. This term here I can represent as a cross product. If that reference frame has an angular velocity omega, I can represent the rate of change of xi hat dt as omega cross xi hat. And you can see that here. If at one time xi hat here, it's another later instant time here, it rotates like this. The difference is going to be along the same direction as dxi hat dt. Okay. So then that allows me to take this expression here and write out this term here. Now again, my vector is q, and the system is rotating with an angular velocity capital omega, and so instead of having a little omega, I'm going to put capital omega. So this gives me a nice relationship between a rate of change in the fixed reference frame to the rate of change in the rotating reference frame. And then what I did was I just rewrote this as an operator, okay, which I'm going to call d dt s naught. It's going to equal to the rate of d dt in the S frame plus omega, then I have to operate on whatever that thing is. Okay, so that's what I have. Next thing what I want to do is I want to use that to get F equals ma. So in my rotating reference frame. So we're going to start off with, we're going to say mass times acceleration, but what I want to do is I want to rewrite that. Mass times d2 r dt squared, and that is in my fixed frame is equal to the force. Okay. So what I'm going to do here is I'm going to start off, but I'm going to start by writing this guy here in the fixed frame. Okay. I can rewrite that as two separate derivatives. So that's ddt in the fixed frame, and then dr dt in the fixed frame. Okay. Now, what I'm going to do is for this term here, I'm going to use this result here. And then for this term here, I'm going to use this result here. So let's do the first term. So again, what I'm writing is the acceleration in the rotating frame is going to be equal to, now let's just keep the first term the same. Okay. Let me just check something here. Okay, we're good. And then let me write out in big parentheses. So then this is the rate of change of r in the rotating frame plus omega cross r. Okay. Now, what I'm going to do is I'm going to express this operator using this thing here. And so then I can put another bracket here. I'm going to get d dt of s plus omega cross, and that whole thing is going to operate on the stuff that's in the brackets. So by doing this, what I've done is I've gotten rid of the s. On the right hand side is all in the s frame, which is what we want. Okay, so now, okay, so let's operate. So if I'm going to write ddt on this, that's going to give me the second derivative. Okay, so I can write that as d2r dt squared. That's in the s frame. So that's the acceleration in the s frame. Then what I'm going to do is I'm going to operate with this onto this. Okay, so then that's going to give me omega cross this velocity in the s frame. Okay. Now I'm going to take ddt and operate on this thing here. Now you got to be careful. I'm assuming that omega is a constant, so that derivative is 0. I have to use a chain rule on this. All right. But then when it operates on r, that's just dr dt in the s frame. So I can write this as omega. There's a 0 term plus the cross of this here. That's in the s frame. And notice these two terms are the same. Okay. And the final thing is I take this, operate on this thing here, and that's just this sucker here. So I get this triple cross product. Okay, so that is the acceleration. Acceleration in the S0 frame, written in terms of stuff in the S frame, which is what we want. Okay. So let me erase. Oops. Let me erase all this stuff here. Okay. So now what I want to do, I want to basically use this result to write down F equals ma in the S frame, okay, given what we wrote before for the S0 frame. So what I can say was that, well, But before I do that, let's actually make this notation a little simpler. All right. So here I'm going to call this R double dot in the S naught frame. Okay. And then this is the R double dot in the S frame. Now at this point here, I'm going to, in the end, I don't really want to ever work in the S naught frame. Okay. So, and then at this point, using your book's notation, it's just going to say this R is in the S frame. So we're just going to write it as R. Okay. So I have R double dot there. And then I have here 2. Now remember, there's this term and this term, they're the same. So I'm going to add them up. I'm going to get 2 of those plus, and then I'm going to call that R dot. Again, R dot is in the S frame. And then finally, I'll get this cross term here. Oops. Oops, sorry, that's a vector there. Okay. Now, going back to Newton's second law. Newton's second law tells me this. Okay, but I don't want to write it in the S naught frame, I want to write it in the S frame. So using the term above, I get R double dot. Then I'm going to get a bunch of stuff. Mass times 2 times that plus mass times omega cross R. That equals F. So in the end, what I get is I get mass times acceleration and some other terms here equals F. So these other terms here, I'm going to call these forces, and instead of keeping them on the left-hand side, I'm going to move them to the right-hand side. So by doing that, what I get is I get mass times acceleration in the S frame is going to be equal to the force, the net force acting on the system. And then I'm going to write it as 2 mass times, now remember the cross product is anti-commutative, so I can write this as, I'm going to bring the 2 out in front, and I'm going to write this as R dot cross omega. And then likewise, I can take one of these cross products and flip it. Mass, and the way it's done is you cross one of those guys. Okay. So that's, okay, so then I get mass times acceleration is equal to the force acting on the system. Now what's this thing here? This thing here is, we're going to give that a name. We're going to call that the Coriolis force. So that is the Coriolis force. And then finally, the last term is the, we're going to call this centrifugal force. Centi. Okay. That's my result. Now, take a look. Oops, so it's just, yeah. Okay, so that's what I have. Okay. So basically what we're going to be doing is we're going to do problems, projectile motion problems using this force. All right. Now let's talk a little bit more about this Coriolis and centrifugal term. So let me go back and let's talk about the centrifugal term because we've seen that before. So we've seen the centrifugal force before in a lot of problems where angular momentum was conserved, and we saw it in the form of the angular momentum squared divided by mass radius cubed in the rho hat or outward direction. So the centrifugal force looked like an outward force. The question is this thing here the same thing as that? And the answer is yes. And so the way we can see that is we can take a very simple example. Say I have a disc spinning, and the disk has an angular speed omega like this. Okay, and so say it moves it has a constant angular speed, or this is its angular velocity. So I can say this is equal to phi dot in the z hat direction. Okay, and then r is a radius vector along the radius of the disk that in a polar coordinate systems like that. So now what I can do is I can stick those guys into these terms here. Okay, so I get mass, and then here I'm going to get v dot z cross r, which is rho hat. Okay, and then I'm going to get cross v dot z. Now I'm going to get, just factoring everything, all the non-vector terms out, I'm going to get m rho phi dot squared. Then if you take the cross products, you're going to, well, z cross rho hat is going to give me phi hat, and then phi hat cross z hat, that's going to give me a rho hat. So you can see it's at least an outward force. Okay, so that's an outward force. But we don't have this expression just yet. However, we've done this enough. We showed, using Lagrangian mechanics, that phi is equal to, just from the definition of angular momentum, piece of phi divided by m rho squared. If I stick that into here, I'm going to get m rho, then piece of phi squared m squared rho to the fourth rho hat. But that's going to give me, again, this is the Coriolis of the centrifugal term. That's going to give me piece of phi squared m rho cubed rho hat. That is exactly this term here. So that expression is a general expression for the centrifugal term that we've been seeing all along. So again, what the centrifugal term is, basically it's outward. It's an outward force. And if I'm in a rotating reference frame and I feel an outward force because of it, it's not a real force. It's just the fact that I say, well, there's an outward force acting on me. Well, the problem is I'm using F equals ma in a non-inertial reference frame, so that is not proper, but we can call it a force accordingly. What about this Coriolis term? Coriolis term is a new term. Oh, one other thing I want to mention about the centrifugal term. Centrifugal term just depends on omega. It just depends on omega. And for the Earth, omega is a small number. So, the fact that I'm sitting at my desk right now, I don't feel an outward force because the Earth is rotating. Yeah, because it's rotating pretty small. Okay. But if I was in a amusement park ride, I would feel that because omega would be much bigger. Now let's take a look at this Coriolis term. Coriolis term, let's just write it. The Coriolis term is, so this is my Coriolis term. It's, oh, by the way, sorry, I made a mistake. I said that wrong. Sorry, when I said, no, I wasn't thinking, it's not just omega, it's omega squared. Omega is a small number. Omega squared is even a smaller number than that. So even in the Earth's reference frame, I'm not going to feel this centrifugal term. Even large scale things like hurricanes and cyclones aren't going to see this centrifugal term because it depends on omega squared, which is a really small number. Now let's look at the Coriolis term. All right, so the Coriolis term is 2m r dot cross omega. Now one thing, it just depends on omega, so it's going to be a bigger term, bigger non-inertial contribution. And you can see here that we can rewrite this as 2mv cross omega. So that means that the Coriolis term is perpendicular to both v and omega. All right. So what does that mean? Well, okay, so say, let's look at the northern hemisphere. So you're in the northern hemisphere, okay. And then this is the equator, and this is the North Pole. And then the angular velocity of the Earth points straight up like that. Now say I move directly north. So say I'm on the equator and I move north. So moving north is like this. That's V. Okay. And then V cross omega is going to point to the right. Okay. Or to the, so if you think about it, I'm moving north, my relative direction. This is east. This is south for you at that position, point in space, and this is west. So what I'm going to feel is as I'm moving up, I would feel that the Earth, I would feel force that's pushing me east because of, again, this is east, and this is my Coriolis force here. Okay. Now, really, what's happening is the Earth is rotating under you, but that's another way of looking at it. So the Coriolis term is it's the term that causes hurricanes and cyclones to move in specific directions. It is not what causes the toilet to rotate in a specific direction. That's a myth. All right, it's the toilet that causes the toilet to rotate. So if you take some people say, well, if you take a sink and have it really steady and you let it go, it's going to rotate based on the rotation of Earth. I think that's bung. I don't think that's true. I think you have to have a really steady sink for that to happen. I don't believe everything you hear, but definitely hurricanes and stuff like that. So in class, we're going to do more problems using the Coriolis term and the centrifugal term. And so that's it. We'll talk to you later. Goodbye.